Okay, let's do some easy fluid questions. So we've got a glass U-tube with a uniform diameter of that. This is used to determine the density of oil, as shown in the figure above. The column of water balances the column of oil, so the interfaces A and B of the mercury of the other liquids are the same height. Here's density of water. So here's what's happening. You got three liquids here. Liquid number one is good old-fashioned oil. So you've got some oil in here. Now the oil is in there. But right before the oil, you poured in some good old mercury. Who doesn't like mercury? So the mercury was poured in first. And on this side, you poured in some oil. And on this side, you poured in some water. Okay, and what you did is you poured in enough of each so that the boundaries of mercury formed a horizontal line. That's what's going on here. Okay, both these caps are open. You put the liquids in there. So what we want to do first is to calculate the density of the oil. So here's what, all right, there's a couple ways to do this. Let's do it the easy way. So do you remember doing problems that looked like this? You know, using Pascal's principle, right? The pressure was evenly distributed. Since both of these guys are at the same height, that means the pressure here is equal to the pressure there. Okay, so pressure is equal to force times force over area. Force 1 over area 1 is equal to force 2 over area 2. Okie dokie, but to make it even easier, it's just a tube, and we now have the same area, so the areas cancel out. So now it's just the force. So how much force is there? It's the weight of the two. So let's do oil first. So the weight is going to be m times g is equal to m times g of the water. But we don't know the mass of the water, annoyingly. So what we have to do is we have to split it apart into how mass over volume is equal to density. So that means mass is equal to density times volume. So here's what we have then. So we know that the density times the volume times the gravity for the oil is going to equal the density times the volume times the gravity of the water. Okay, gravity cancels out because, you know, it does. So now we have volumes. So P, or this row is what we're solving for, times volume. This is a cylinder here all the way down. So we're going to have pi r squared times h. The h is going to equal 0.272. This is going to equal the density of the water, which is 1,000, times the volume, which is going to be pi r squared, times h, which is 24.5. Now, these guys cancel out. Don't even need that diameter. All right. So solve in time. So solve. You're going to get a density of 901 kilogram meters cubed. Nice, and that's it for that one. Let's keep moving on. Calculate the pressure at B. So B is this guy right there. So the interface between the mercury and the water. Nice. There's a formula for this. P is equal to P0 plus rho times G times H. This is on your formula sheet, so you should know it. So P is the pressure, absolute pressure. It's the pressure on the top part plus the pressure of the height of the water. What's the pressure on the top? Pressure on the top is atmospheric pressure. You should know that atmospheric pressure is about 100,000 or 101,300 pascals, plus water has 1,000 times 9.8 times H, which is 0.245. Multiply, and add, you can get 103.7 kilopascals. You could have done 103,700 pascals, whatever, it's all the same. Okay, so that's all you got to do for that one. So over here, a new tube identical to the U-tube, except for the cone shape is above to the left. This one's A, this one's B, before I forget. It's filled with the same volume. Okay, same volume of mercury. The mercury is at the same height of both sides as it was before. The same volumes of oil and water are poured in to the left and the right, just like before. So here's our oil, here's our water. So looking at B, is B going to be up, down, or the same? Now remember, it depends on pressure like we talked about before. Now, this side is going to be identical. Since this side's wider, it's going to have the same volume, it's going to be shorter. Now, since it's shorter, because remember, pressure is calculated by rho GH, H went down, so pressure went down. Okay, since pressure went down, this side is going to push more. So B is going to be below A. All right, justify your answer. Well, I just told you. H decreases, so pressure decreases, so it moves up. So moves up. We're talking about A here. So A moved up, B went down. Okay, next one. New tube is identical. Here's A and B. There's oil and water. Okay. A small piece of wood with the density less than that of oil is placed so it floats on the left side of the tube. Indicate whether the pressure at the bottom of the tube will increase, decrease, or stay the same. Okay, so water's the same. So for my oil, we put a block of wood in there. It's just going to float. All right. So what's going to happen here? So this will cause the height to go up, right? Because the wood will push the water, the oil out a little bit. So, just like when you put ice cubes in water, the water goes up. So since the height goes up, what does that do to the pressure? The pressure is going to go up as well, increase. You don't even have to justify that, but there you go. That's it for that. Like and subscribe for more videos coming soon.